Hi, hello, this is Srija from CSD C section department. I am here to say about skew symmetric differentiation matrices. The theory of finite difference methods for discretized partial differential equations is mature and well understood, the mainstay of numerous computational algorithms for the past century. It is a sobering fact, however, that even in its basic linear setting, this theory is incomplete. The theme of this paper is an interesting lacuna in the classical theory, a good starting point in the convection diffusion equation. Bajan 2004, Morton 1996, in a univariate setting. Dow u dow t is equals to dow 2u dow into 2 plus v into x dow u dow x comma t greater than or equal to 0 comma x belongs to open in closed interval minus 1 comma 1 accompanied by an initial condition for t is equals to 0 and Dirichlet boundary conditions at x is equals to 0 and x is equals to 1 where the average transport velocity v is a given smooth function. The equation 1 comma 1 is important because it's multivariate generalization. Dow u dow t is equals to 2u plus v into x u comma t greater than or equal to 0 x belongs to 0 comma 1 d is a model for transport phenomena combining diffusive and convective process. A powerful means to solve 1.1 easily extended to a multivariate setting is through an exponential splitting method NC Lachlan and Quipsel 2002. Its simplest manifestation, the string splitting, approximates 1.1 by the time stepping un plus 1 is equals to e12 un plus 1 is equals to e12 delta t into c is e delta t into d2 e12 into delta t c un plus fn where n greater than or equal to 0 where u n m approximate to u into m delta x comma n delta t comma d2 is a second differentiation matrix, that is an approximation to the second derivative using a linear combination of grid points, while c is the outcome of multiplying each mth row of the first differentiation matrix d1 same by Vm delta x. The inhomogeneous vector Fn consists of boundary contributions Hochberg and Osterman 2010, Isserles 1992, and we note that Fn equal to 0 with the Dirichlet boundary conditions are 0. Since E12 into delta T C E into delta T D2 E12 into delta T C is equals to E delta T into D2 plus C plus 0 into delta T into 3. The method is second order in time, therefore it makes sense to discretize in space to a similar order. This is the case with the familiar differentiation matrix. D1 is equals to 1 by delta x. This is a 4 by 4 matrix which consists of 4 columns and 4 rows. 0, 1 by 2, 0 and 0. Minus 1 by 2, 0, 1 by 2. So then d2 is equals to 1 by delta x into delta x whole square minus 2, 1, 0, 0, 1 minus 2, 1, etc. It is important to emphasize that the absence of high order skew symmetric differentiation matrices is purely an artifact of Dirichlet boundary conditions. Once we consider periodic boundary conditions and are allowed to wrap around the matrix D1, We can easily generate skew symmetric matrices of any order. For example, U dash m approximate to 1 by delta x into 1 by 12 um minus 2 by 3 minus 1 plus 2 by 3 plus 1 minus 1 by 12 plus 2, where m is equals to 1 to capital M, where delta x is equals to 1 by capital M represents a fourth order scheme. Once we wrap around boundaries, that is, identify M with M mod M, the outcome is the skew symmetric banded circulant. This is a one more matrix where D1 is equals to 1 by delta x. Now, on stability and skew symmetry. Let U be a smooth function for x belongs to 0, 1. Set um is equals to u into m delta x. u0m is equals to u0 into m delta x for m is equals to 0, 1 and so on up to n plus 1, where delta x is equals to 1 by m plus 1, and consider the approximation. The underlying differentiation matrix D1 excludes boundary conditions, thereby is of the form D1 is equals to 1 by delta x into B, where B is equals to B1, 1, B1, 2 and so on up to B1, m. In second row, B2, 1, B2, 2 and so on B2, m, and so on row m, bm, 1, bm, 2 and so on bm, m. The coefficients bm, k may themselves depend on capital M, but in the interest of clarity, we suppress this dependence in our notation. The semi-discretization 2.1 is stable in the sense of flags if assuming 0 Dirichlet boundary conditions u0, um plus 1 is equals to 0. It produces a solution vector u into t, which is uniformly bounded in the 2 norm in every compact time interval. As is well known, stability is equivalent to the statement that e to the power delta t by delta x into b less than or equal to 1 plus alpha delta t for some alpha greater than or equal to 0 uniformly for delta t comma delta x tends to 0, provided that delta t by delta x is bounded away from 0 and infinity. Iserles 2008. It is important to recall that unless B is a normal matrix, 2.2 is not a statement on its eigenvalues specifically, and is not sufficient for all the eigenvalues of B to reside in a shifted complex left half plane. We must instead consider its logarithmic norm, Soderlund 2006, u mu into B, namely the largest eigenvalue of the symmetric matrix B is equals to 1 by 2 B plus B power t. It is well known that e power tb greater than or equal to e power t mu into b, comma t greater than or equal to 0. For some alpha greater than or equal to 0, uniformly for delta t comma delta x tends to 0, provided that delta t by delta x is bounded away from 0 and infinity. Iserles 2008. It is important to recall that unless B is a normal matrix, is not a statement on its eigenvalues. Specifically, it not sufficient for all the eigenvalues of B to reside in a shifted complex left half plane. We must instead consider its logarithmic norm, mu into b, namely the largest eigenvalue of the symmetric matrix B. 1 by 2b plus b power t. It is well known that e power t b greater than or equal to less than or equal to e power t mu into b, where t greater than or equal to 0, and that mu into b is the least constant consistent with this inequality. Therefore, 2.2 is equivalent to the statement that mu into delta t by delta x into b less than or equal to alpha delta t. Therefore, mu into b less than or equal to alpha delta x for some alpha greater than or equal to 0. Clearly, if B is Q symmetric, then mu into B is equals to 0 and stability is assured. Suppose, however, that for every m we have mu into B is equals to Km, comma Km greater than 0, and that limit SUP m tends to infinity, Km less than greater than 0, then 2.1 is unstable. As an example, consider amending the differentiation matrix form 1.3 by replacing its first and last row by mu dash 1 approximate to 1 by lambda x into minus 1 by 4 mu naught minus 5 by 6 mu 1 plus 3 by 2 mu 2 minus 1 by 2 mu 3 plus 1 by 12 mu 4. Mu dash m is approximate to 1 by delta x minus into minus 1 by 12 mu m minus 3 plus 1 by 2 mu m minus 2 minus 3 by 2 mu m minus 1 plus 5 by 6 mu m plus 1 by 4 mu m plus 1. Respectively, note that order 4 is retained because we are considering Dirichlet boundary conditions. Delta x is equals to 1 by capital M plus 1. We have, therefore, it is a 3 by 3 matrix. B bar is equals to B1 bar 0 0 0 0 0 0 0 B2 bar. Where B bar 1 is equals to minus 5 by 6, 5 by 12, minus 5 by 24, 1 by 24. 5 by 12 0 0 0 minus 5 by 24 0 0 0 1 by 24 0 0 0 comma b bar 2 is equals to, it's a reverse of b1 bar 0 0 0 minus 1 by 24 0 0 0 5 by 24 0 0 0 minus 5 by 12 minus 1 by 24 5 by 24 minus 5 by 12 and 5 by 6. Thus, B bar departs from 0 in just 8 columns. Actually, it is a rank 4 matrix whose non-zero eigenvalues are plus or minus 5 by 12, plus or minus under root 226 by 24, comma Km is equals to mu into B is equals to 5 by 12 plus root 226 by 24 approximate to 0.886, and the matrix corresponds to an unstable method. Our discussion helps to exclude non-skew symmetric matrices B from further discussion yet. Even if B is skew symmetric, we are not done yet. Recall that the purpose of the exercise is to discretize mu into x dou by dou x rather than merely dou by dou x. Thus, we assume that mu is a given smooth function. Let mu m is equals to mu into m delta x and approximate mu dash m by multiplying the right hand side of 2.1 by mu m comma m is equals to 1 and so on up to capital M. In other words, our interest is in stability of the matrix C such that Cm comma k is equals to mu m bm comma k comma m comma k is equals to 1 up to so on capital M. Skew symmetry of B is still necessary, of course, because of the trivial case mu is equals to 1, but we cannot take for granted that it is sufficient for all functions mu of interest. Now, it's a theorem 1. Let the matrix B be skew symmetric and bounded, that is Bm, K is equals to 0 for det m minus k greater than or equal to r plus 1 for some r greater than or equal to 1, and let its coefficients be independent of m, then the matrix C is stable. Proof: because of bandedness and skew symmetry of B, we have C bar m comma k is equals to bracket 0 comma m is equals to k, or det m minus k greater than or equal to r plus 1 1 by 2 mu in m minus mu k 1 by 2 mu m minus mu k into bm comma k 1 less than or equal to det m minus k less than or equal to r, where c bar is equals to 1 by 2 c plus c transpose we call Gregorian theorem. The eigenvalues of the m into m matrix reside in the union of the discs Sm into A is equals to bracket z belongs to C det z minus am comma m less than or equal to summation k is not equals to m det am comma k m is equals to 1 up to so on capital M. Therefore C bar being symmetric, mu into C less than or equal to max bracket x belongs to R intersection Sm into C bar, where m is equals to 1 and up to so on capital M is equals to maximum m is equals to 1 up to so on m, summation k is not equals to m cm bar comma k. However, since mu into x minus mu into y less than or equal to mu dash infinity x det x minus y is equals to summation k is not equals to m det c bar m comma k less than or equal to 1 by 2 summation m minus k less than or equal to r det um minus uk det bm comma k less than or equal to 1 by 2 mu dash infinity delta x summation det m minus k less than or equal to r det m minus k into det bm comma k. We commence from s is equals to 2.3.2 results in summation m minus 1 k is equals to 1 k square b k comma m plus summation m k is equals to m plus 1 k square bm comma k plus m plus 1 square cm is equals to 2m, where m is equals to 1 and up to so on capital M. And substituting the values of cm from 3.3 yields, we get these type of equations. These values are substituted back into 3.4 for m is equals to capital M. We obtain on the left hand side, those are these equations. Because the sums in the square brackets match each other, we recover the right hand side of 3.4 and all is well. P is equals to 2 is satisfied. We proceed in an identical manner with s equals to 3, and this is the moment things turn sour. The order condition 3.2 is now. So the equation is this, and substituting 3.3 results in the equation is this. For m is equals to 1 up to so on m capital M, next we substitute b m comma k m comma small m is equals to 1 up to so on m minus 1 from 3.5. After elementary algebra, we obtain this equation. For every m is equals to 1 up to so on m minus 2, we solve 3.6 for b m comma capital M minus 1. We get these type of equations. The two sums above are identical ones. We swap indices, hence they cancel. The left hand side is thus 1 by 24m into m plus 1 into m plus 2. The right hand side of 3.6 for m is equals to m minus 1 is however 5 minus 3m. It is easy to verify that they fail to match for all m greater than or equal to 1. So, with this session, With this, I end this session. Thank you.